So looking at this example then, let's follow the same idea that we did a minute or two ago. I've got a problem, I look at it, I read it. That's what I'm after. And I remember this other little formula here that tells me how to work out the safety factor. So to get the safety factor, I'm going to need the maximum shear stress and the applied shear stress. What am I told? Am I told the maximum shear stress?
Yeah, 140 meganewtons.
Right, that's this effectively, isn't it? The failing stress for the material. So that's the maximum, that's tau max. What else am I told about this thing? What's this here? The power, 150 kilowatts, is the power. Ah, I've got a formula that relates to power, that's got something to do with the power. What's this? Sorry? 1,650 RPM. Not velocity. To do with it, the frequency. RPM means revolutions per minute. The frequency in hertz is in revolutions per. So I can work out the frequency by dividing that by 60, and that will give me the frequency. Let's look back at other formula that we know. Oh, look. If I know the frequency, I can find the angular velocity. If I know the angular velocity and the power, I can find the torque. So I can actually find the torque. This is what's going through my mind, because I know these formulae. So, oh, right, I can actually find out what the torque is, because I know that and that. So now, whoops, wrong way. So now, with this information, what pops into my head as soon as I see something like that is, power and frequency means I can actually work out the torque. And I know the maximum stress. I know made a steel tubing with an outside diameter of that and an inside diameter of that. So what else can I work out? Look back at the other formula we've got. J, I hear somebody say, yeah, I can work out J. So I've got this formula. Which ones am I going to use? Which two ratios? First and second, yes. I must use the second one. Why? Because that's what I'm after, isn't it? The applied shear stress. I know R, it's half the diameter. I know how to find T, the torque, and I know how to find J. And so this is the one I'm going to use, nothing to do with this. So I rearrange that ratio for tau, and then I work out what T, J and R are and plug them in. Okay? I'll just pause this for a little while and have a look at it, and then we'll look at it together. So I'll write down what I know, get the units correct, and then think about the formula. This is the formula, rearranged for tau, which is what I'm after, the applied torque, shear stress rather. Now remember, I need a way of finding out what is this T, what formula allows me to find T, what formula allows me to find J. This is my thought process that I'm going through. I'm not saying you must do it this way, but this is one way. Work out what T and J are, plug them in. So I know that power is torque times the angular velocity, omega. So rearrange for the torque, it's power over the angular velocity. I don't know that, but I know a formula that does. 2 pi f, and I know f, so I can work that out. Similar for this, I know a formula that allows you to find j, which is one of those set formulas they had. D to the 4, is it? Minus d to the 4 over 32, something like that. If I remember that correctly. Times pi. So I know the outer diameter and the inner diameter, so I can plug them in, and out comes the answer. So with the values given in the right units now, check those. The radius we take to be half the outer diameter, which is that. And then we can plug the numbers in. So we get a value for T equal to 868 Newton meters and J equal 1.83 times 10 to the minus 6, did you say, David, or minus 3? Minus 6. Yeah. Meters to the 4. Now I can put those values into there to get the tau applied. So tau applied is, so the safety factor we can work out. Tau applied turns out to be 17.75 meganewtons per square meter. Tau max is 140 meganewtons per square meter. So they're both in the same unit, so that's all right. So just divide 140 by 17.75 and we get
3.8.
So call it 8. Safety factor's about 8. Is that typical?